All right, so previously we created a forward checking algorithm that would make sure things could exist within the context of their environment before being placed. And now we need to create an algorithm that will remove things that have been placed and create an unsolvable graph. So for an example is, it's kind of hard to show a backtracking necessity within this tile set as it is so simple. However, let's say this was placed right here. This is an issue because there is no way for this to be solved. There will be no tiles that can exist to make this solvable within our tile rules. Um, so we need to find a way to go ahead and remove that and try again, and then we could come back and move on and see that everything can still work out. So we're going to use backtracking. Now, before we do that, there are a few things we need to mention. First being, I've made some changes. The first change within the collapsed cell, there was a branch here that checked the length of the collapsed tiles. It looked like this. And I've gotten rid of this as this check, it functioned for what we needed. However, it will not work later on with multiple chunks. So we can just go ahead and get rid of that. And instead we need to make sure that within the remove from entropy array, we do a branch check, checking the length of the tile set at the cell index we're trying to remove is less than or equal to the length of our entropy array. And if that's true, then we can go ahead and remove from the entropy array how we have it set up. And if that's false, we can ignore it. And that solves the issue where our first tile has a, if we come and look at it, where is it, propagate collapse, the first tile we're going to select from will have a length of 9 for its tile options, the tile set, and therefore it will get ignored and not try to remove it from an entropy array, as it doesn't exist within an entropy array right now, and the entropy array, it never gets to a length of 9. Perfect. So the next thing we need to do is make another change. After the forward tracking, we had another boolean that checked a output called the break bool. I've gotten rid of this and instead moved it inside of forward checking, as it keeps things a little bit more clean. So I have gotten rid of the break bool as an output and instead just placed it right here. We're checking as long as the break bool is not, as long as that's true. So this is a little bit of backwards logic. Then we can continue with the algorithm. That means if we do, for whatever reason, break this for loop with breakout, which will happen with backtracking, we will not continue down the algorithm chain, as this completed will always fire even if we break a loop. Now that could be changed within the macro, but we'll just leave it like this for now. And then, oh, that's right, within forward checking, we also need to come over to the right. There was a huge blunder that I made, and I'd have a separate video covering this. This right here was incorrect. I had copied over my own implementation incorrectly and left this as such. We have, when the create and check new tile options is ran, it's making sure that our neighbors options, at least something matches up with the wanted to be selected tile, and as long as that's true, we would be able to continue down the algorithm. If that's false though, there are no valid neighbors, and there's no valid options from the neighbor for our rule sets. We were going to go ahead, get this set ref, remove the selected tile being within the collapse cell. This is the selected tile, so it's from our weighted selection. We're going to remove that from what I had meant to be the current tile options. However, what I did was I left it as just set ref, which is actually a direct reference to our neighbor's options. This is a huge error, because we're then removing our selected tile But we're not only doing that, we're also checking if it's not empty, and that's good. That'll be for backtracking. But we're then resetting the options that should be at the current tile action to set ref, which is now set to our neighbor's options. So we're overwriting what should have existed as a completely different tile set. Instead of our current options minus the one that doesn't work, it is now our neighbor's options minus the one that doesn't work, and no longer even the what should have been -1. So it's entirely incorrect and would cause massive errors. So we need to make sure that this comes in here and the set ref gets set, or you could just alternatively do that right there. However, I tend to set outputs of our finds, because every time we need to, because we're going to use this set ref multiple times here, here, and here, that reduces the number of calls using the find to just one. So instead of finding every single time, instead of having this plugged into here, here, and here, where we would have to then run the find node 3 times, it will only be ran once for setting that. And this is near instant. This does cost some time within the Unreal framework. Okay, so that should be all of the changes. So let's go ahead and hop into backtracking. First thing we need to do is go into our structs and enums, add in a new struct, right click, blueprint structure, and that will be the WFC save struct. So what its new name is: 4 variables, entropy array of type int array, map of tile options of pin type integer values tile structure, collapse tile map, that's integer and tiles, and then our seed of random stream. So this is going to be where we save our state. We're going to literally come in here and we're going to save every time a tile is collapsed. We're going to save everything that exists. This will be fairly expensive, but it's a quick implementation for now. And so we're going to leave it. I'm going to leave this as is for now. So make sure you have that structure. Then we'll need 3 variables: save state, type integer, and then the value of our new structure, 2 integers, backtracking attempts, and collapse cells since backtrack. Perfect. Now within the collapse cell function, we're going to actually save the state, and this will be done upon entry into collapse cell. We're going to check if backtracking attempts is equal to 0, and this is going to stop us from saving the state when we are currently backtracking, and or if we're doing multiple backtracks. This will stop us from saving states that we've already found will lead to a failed graph. So as long as this is equal to 0, that means we're not backtracking, no backtracking has been attempted. Then we're going to go ahead and add to save state at save state length. And this adds, so we can quickly find it. It's kind of using a map as an array. So trying to think, I think I used to have more specific use cases for why this was a map, but you could probably just use this as an array. So, what was I saying? That's right. We're saving it at length, and that makes, so if this is empty, then it will be saved. This length of 0 will be saved at 0, the first one, and then if it's a length of 1, that means it'll be saved at 1, and so on. So we can quickly access things, functioning essentially as an array. We just need to add each of our variables. That's the entropy array, tile options, collapse tiles, and our seed. Seed is important, as if we backtrack and don't have the correct seed, generation will be different and cause errors where seeds are getting a little bit funky. Perfect. Next thing we need to do is within forward checking, we need to, over here on the right side, where we check if the set ref is not empty. That's false. That means this set ref is empty. That means there are no more options within this, our current cell's tiles options. That's kind of a horrible name. That means nothing will be able to be placed, so we need to backtrack. And this will be done by first using a sequence off the first, execution pin, pulling that all the way back here to the break. So we'll stop any more of this for loop running, and then running our backtracking function. So make sure you add a function, and you can print something like backtracking. Within here, we will see the first thing we do is we get the save state length -2 and make sure that's greater than 0. And if that's false, that means our save state doesn't have any more states to go back into, any correct states. We go back to, because a save state -1 would be this state that we just saved. So it would be this one. And if we're backtracking, this means that this is corrupted, or it leads to an impossible scenario. So we don't want to look at this one. It would just be an unnecessary call, ending up with a bunch of collapse graphs there. So -2. If this is false, that means that the entire chunk, this chunk in its entirety, doesn't work. So we would then actually need to do some chunk backtracking, which would use a similar idea. Because the convenient thing about wave function collapse is essentially chunks are the same as a tile, because it's just like a square, at least using simple geometry for a. I mean, if this chunk doesn't work, then we just need to backtrack the whole chunk and go to another chunk. And if that chunk doesn't work, keep going back till we find one that does work, and then retry all the generation, which is exactly what we're doing, just on a micro scale. So the micro and the macro function almost identical. For now, we'll just call the failed variable. I think I mentioned this previously. It's just a variable I use over here in the propagate collapse. You can use this to stop the while loop in case there's any debugging and you don't want things to continue. So that can work a little bit nicely. Then we need to increment up backtracking attempts set collapse cells since backtrack to 0. Now, what this will be used for, and we'll see in a second, is it is going to be our kind of dynamic approach to getting out of a backtrack. Once it'll help us find when we are outside of the broken graph and we are now within a generation that is functioning. And the next thing is finding from save state. We want to get that save state length -2. We're setting it, so I'm just pulling up here using a promote to local variable. I'm doing this instead of breaking, because if we were to break and then pull off each of these, every time we set one of these, it will come in here, it will get the corresponding variable, and then it will call it'll have to call this find. So we would have to call find 4 times versus the 1, like I mentioned with the earlier reference I was using. So that's why we're promoting the structure. And find nodes can get more expensive with structures too, so this is helping to mitigate that. And this does make a difference. Every time we're doing this is improving the algorithm. Finally, we need to remove the save state -1. That was the save state that leads to a failure, so we don't want that, so we'll get rid of it. And then within collapse cell, we need to create an out. Once we are no longer within the backtracking timeline, we'll call it, we need to make sure that we indicate that so we can start to save our states again. And you can think of this too. The importance of this is if something were to happen like this, where we have these tiles that can't exist, but our generation continued regardless, and then it eventually got here, and then was going to try to collapse this cell, and found that, oh, there's nothing that can exist here. We don't need to just get rid of one tile. Technically, we need to, I mean, we could get rid of just that tile, and you could try to make a more dynamic approach that would solve what tile is actually causing the problem, and that would potentially be more efficient. I don't have a setup like that right now. That could be something kind of cool because we know this is the problem, and there could be approaches to solving that and like figuring out this specific tile, then getting rid of it. But right now, the approach is just going to be, oh, we've collapsed all these cells, so we need to go back and get rid of each of these and then get rid of that one and try again. So we're not just doing one backtrack, we're doing multiple until we get back to this state. And that's why this also helps, because our backtracking attempts may go upwards of 2, 3, 4. We'll see. I'll give you an example. It goes 53 times. So, yeah, we need to make sure that we don't accidentally save the state while we're backtracking and then that throws in another state that we have to try to solve for and find out it doesn't work and just keep going, and that could create looping bugs and infinite loops potentially. So once we know we're in the clear, we're going to go ahead and set the backtracking attempts back to 0, which will then allow us to start saving states again. So that's going to be done over here. At the very end of the collapsed cell, run another sequence. This is my print debug. I think I briefly showed it. It's very not important right now. But we need to run a branch. The branch is checking if the backtracking attempts is not equal to 0. So that means that we have tried to backtrack at least once, and therefore we need to increment the collapsed cells since backtrack. And we're doing this here because if we've gotten to this point within collapsed cell, that means we've also gone through forward checking and there was no more backtracking triggered. So everything is clear so far. And so we're going to increment this, and then we're going to continue. Wait a second. Wait, this is wrong. Yeah, that's not correct. We need to do that. Okay, give me just a moment. Let's see if that breaks everything. That shouldn't. Yeah. Okay. Sorry, that was an incorrect pinning. Perfect. So, okay, bear with me. I'm not going to edit this out. I'm actually going to double check. I had done this, but now I realize that I don't like this. That's right. Let's see if this breaks everything. Okay, no, we're good. Perfect. So next thing we need to do is then do another check and see if the collapsed cells is greater than the backtracking attempts. So that means that we have successfully gone through, we've successfully performed a collapsed cell. So we're going to track and count how many of those have occurred. And then if we have successfully collapsed more cells than we've attempted backtracks, we can set this back to 0 and then start to save states again. That's just, it's counting, let's say, so we had it right here. We just, let's say we do that. So there's 2 cells that have been collapsed incorrectly. So we're going to go here. We're going to clear that. It's going to then, oh, I guess, I'm sorry. I'm getting a little obvious. Okay, right here. So this backtracks. This algorithm's not very efficient. It's so this is going to be a perfect example of why it's not. So we're going to try to collapse this. We see it doesn't work. We'll remove this one, and then it's going to essentially resolve it and find that, oh, that wasn't the cell because we've still ended up here. So it'll get rid of that one, and then that one, and then it'll place them again. See, oh, 2 cells have collapsed now, but we've now backtracked 2 times as well. So we're going to backtrack again. This is now the 3rd backtrack, and we're going to be in the clear because it's going to collapse this cell, and then it might collapse another cell, and then it might collapse another cell, and that's now where we had backtracked 3 times, it's now collapsed 4 cells. So we know that we are definitely in the clear. If that makes any sense, you can see where this doesn't work the most efficiently, because it has to check still every single cell where we are collapsing them still, regardless of if they're the problem or not. This cell isn't necessarily the problem, and I don't really like that, and I will probably come up with a better solution in the future. Backtracking is just pretty low on my list of priorities right now. I just need something that works. So we'll have to get rid of that one, and then it would still collapse it and still find that problem. So it'd have to go back again, and it would probably still collapse things. And but this could even end up in a different error where it collapses other cells and finds that, oh, we still end up here, so it'd have to go all the way back until eventually it reaches that and gets rid of it. So, well, like I'm saying, don't expect this to be the best algorithm, and I would challenge you to try to create your own that works a bit better, and that will be something I deal with in the future, but for now, this works fine. It'll get there, and we can see that by my quick little thing I was doing there. I was making sure everything was running when I made that change. So up in the top left, we see backtracking 1 times. In my own implementation, I'm injecting in a incorrect cell that will cause a backtrack, and we'll see that it had to backtrack 10 times to solve it. Just 1 time, 20 times for that. 1 time, and then the big one right here is 53 times. So there had to be 53 backtracks to solve this chunk, and you can see it did all sorts of counts. It was going through, had to go all the way back, but it did solve it in the end. And while I was redeveloping this, because I had to overhaul the whole backtracking, I tried to do that for every function I put a video out on. There were times in which chunks would get caught in weird loops where they were getting to solvable states, but then eventually hitting a error. They were hitting an impossible and then having to go back, but they weren't catching the correct cell, so it kept looping through, but eventually reached there. It could take a little bit of time. So I really want to push this idea that this is not going to be the perfect implementation. This works for a very simple wave function collapse for now, though. So this video is now 22 minutes. Not a huge fan of that. However, I hope that makes sense. Please feel free to ask questions, and I'll see you in the next one.